Hey, good afternoon, everybody. My name is Pete Ewell. I'm a PhD student here in the Computational Science Research Center, and I work with Professor Naveen K. Vaidya. Today, I'm going to be talking to you about mathematical models for cystic fibrosis. And so cystic fibrosis is caused by a genetic defect that interferes with the transport of water across cell barriers. And the result of this is that many bodily fluids become very thick and slow moving. And in particular, what CF is most well known for probably is this thick buildup of mucus in the lung airways that interferes with airflow and causes difficulty breathing for people who have CF. This mucus is also very nutrient dense, nutrient rich, and can be colonized by different types of bacteria. And some of these bacteria are known to be more pathogenic and cause more severe illness. So we're interested in being able to characterize the populations of these different kinds of bacteria and understanding what causes the more infectious ones to proliferate. So today I'm going to be showing with you some ordinary differential equation models and a few agent-based models. So our ordinary differential equation models, we consider two populations. We have what we call the climax bacteria first, which are mostly aerobic and not as pathogenic, so they don't cause quite as severe illness. And then we have the attack bacteria, denoted F, which are known to cause more severe illness. We know that oxygen is a very important component in the dynamics of these two bacteria because the attack bacteria are made up of facultatively aerobic bacteria and anaerobic bacteria. So oxygen kills some of the attack bacteria, but the climax bacteria need oxygen to survive. So on the right here, I have a schematic of the dynamics of these two populations. We have the climax bacteria C, the attack bacteria F, and they're competing for the available space in which to grow in, so which would be K. Both populations are being created at certain rates, RC, and so for climax bacteria, we know that their growth rate is a function of oxygen, and we also know that oxygen kills some of the attack bacteria. We also know that just these bacteria are dying naturally at a certain rates. And so this schematic gives you an overall description of the dynamics in our ODE model. So in addition to this ODE model, we develop some agent-based models. So on the right here, I have a figure of some data that we were able to fit our models to. So this data is from a patient at the University of California, San Diego Adult Cystic Fibrosis Clinic, undergoing what's called an exacerbation event, which is where the attack bacteria are growing over time and causing more severe illness. So this data is taken over a period of about 40 days. And at the beginning of the time frame, the attack bacteria are slowly increasing, which is causing more severe illness. And then at a certain point, about 28 days into this time frame, the patient started receiving antibiotic treatments that came in and started killing the attack bacteria. So we fit our ODE model to this, and then we used our ODE model to develop a spatially homogeneous agent-based model. And we're doing that because in reality, the dynamics of these two populations depend on where the bacteria are located in space. So we wanted to consider spatial dynamics too. So in this next slide, I have a simulation of a spatially dependent agent-based model. So on the right-hand grid here, we have our bacteria. So purple bacteria are climax, yellow squares are attack bacteria, and black squares are empty. On the right-hand grid is our oxygen dynamics. So the climax bacteria we know consume oxygen. So areas that are very rich in purple squares are going to be lower in oxygen because the climax bacteria are consuming it. And that is going to give an opening for the attack bacteria to come in and colonize that region. So one of our goals we have for this work is to develop an optimal antibiotic treatment regime to come in and lessen the frequency of hospital visits by lowering the overall proliferation of the attack bacteria, which we can do because we know clinically we have antibiotics that target the attack population. We also, at some point, we're working in collaboration with the Viral Information Institute here at SDSU. Eventually, we're going to be wanting to develop phage therapies to target the bacteria that we know to be the most pathogenic. So quickly, I'd like to acknowledge some people at the VII, Cynthia Silvera, Doug Conrad, and Forrest Rower for providing the data that I fit the models here to today. And I'd also like to thank Dominic Wadars at UC Irvine for instructing me in the design and use of these agent-based models. Thank you. I look forward to your questions.